Hi everybody, um, Professor O here, uh, putting together another video for you for Chapter 12, our Fundamentals of Graph Theory chapter. So I just thought I'd go through some problems like I have in the past, some selected problems, and show you some of my solutions for them. So we're going to start here in section 12.1, number 16. So this problem asks, gives us some information about a graph and asks how many vertices have degree 3. So in this graph, we know it's order 25, it's size 62, and every vertex has degree either 3, 4, 5, or 6. It tells us there's 2 vertices of degree 4 and 11 vertices of degree 6. How many vertices of G have degree 3? So this is what we got to answer right here. How many vertices have degree 3? So this is a pretty standard application problem of the first theorem of graph theory. Remember, the first theorem of graph theory says if I add up the degrees of the vertices in a graph, so if I do the sum over all vertices in the graph, that I will get twice the size of the graph, so twice the number of edges. It'll look a little bit different in your book, but that's the idea. So if you add up the vertices, add up the degrees of the vertices, you get twice the number of edges. So here we have the number of edges. Remember, that's the size of the graph is 62. So when I add up all the degrees, I should get, 124. So what this is telling me is 124, so twice the number of edges, is equal to the sum of the degrees over all vertices in the graph. It's order 25, so I know there's a total of 25 summands here in this thing. And I can split this up in terms of the degrees since I already know some information about the number of vertices of degree 4 and degree 6. So let's go ahead and get those in there. Well, I guess to make this as clear as I possibly can, let me write it like this. So equals, so number of degree 4 times 4. So the number of vertices of degree 4 times 4, that'll be the sum of all the vertices of degree 4 plus number of degree 6 times 6 plus number of degree 3 times 3 plus number of degree, what's the remaining one? 5 times 5. So that's what my sum is going to look like, and I know how many degree 4, how many of degree 6. So let's go ahead and get those in there. So 2 vertices of degree 4, that means I'll get 8 for this particular sum. And I have 11 vertices of degree 6, so I should get 66 here for the sum of those degrees. And then I don't know how many vertices of degree 3 or vertices of degree 5, so I'm going to give variables to those. Whenever I have some unknowns, it's wise to give variables to these. So I'm going to let x be the number of vertices of degree 3 and y be the number of vertices of degree 5. Then that part of the sum looks like 3x plus 5y. So let me simplify this a little bit. What do we have here? We have 74 plus 3x plus 5y, and we know that should sum to 124. Let me go ahead and subtract that 74 over, so this is 50 equals 3x plus 5y. So what this is saying is when I add up, this part of the sum, I should get 50. That's the information I've been able to synthesize so far. So I have this relationship between x and y. Of course, this is just one equation of 2 variables, and so this can't be solved outright. This would tell us there's various possibilities for x and y. However, we know another relationship between x and y. What haven't we used yet? That the order is 25. So I had how many vertices of degree 4 again? I had 2 vertices of degree 4. I had 11 vertices of degree 6, so that's 13 of degree 4 and 6. And so there must be 12 left over. We know there's 12 vertices in this camp that are either degree 3 or degree 5. X is the number of vertices of degree 3, y is the number of vertices of degree 5, and so that's telling me that x plus y has to equal 12. So we also know x plus y equals 12. So now I have 2 equations of 2 variables, And so this is a system of equations that I can solve exactly. Since I'm interested in knowing x, remember the number of vertices of degree 3, I let b equal to x. So I want to have x equal to something. And so what I'm going to do is I'm going to solve for y in this equation and then substitute it over into this one. So this is y equals 12 minus x. And I'm going to go ahead and substitute that in for y over here. So this tells me that 50 equals 3x plus 5 times 12 minus x. All right, let's work this out. 3x plus 60 minus 5x. So what I'll get, negative 10 when I subtract that 60 over equals negative 2x. Good thing both sides turned out negative, so that x will be positive, which we know it must be. Divide by negative 2, I get 5 equals x. And therefore, I mean, I can answer my question right here. So there's 5 vertices of degree 3. We know that has to be the case. I can go ahead and back substitute if I want. I mean, I'm done with this question, but I could take that 5 and put it back up in here and know that this implies y is 7. And so I can gather a little bit more information. So that would be 7 vertices of degree 5. Notice that the odd vertices, the ones of degree 3 and 5, there's 12 total of those. So that's an even number of odd degrees, and so that checks out. Remember, you can't have an odd number of odd degree vertices in a graph. All right, so that's that one. Pretty cool, right? Let's jump over here to problem number 20 from the same section, 12.1. In this one, we're asked to construct some graphs with given properties. We know that each graph, G1, G2, and G3 is order 7, and that every vertex has degree 2, 3, or 4 in each graph. Furthermore, there's at least one vertex of each of these degrees. And then in part A, we want at least 3 vertices of degree 2. In part B, at least 4 vertices of degree 3. And part C, at least 3 vertices of degree 4. So while looking at your homework for this section, I noticed some people starting off in a nice way. They just started with a 7 cycle, so C7. And then they started adding edges to this. So there's 5, 6, 7. And they just started by connecting these in a cycle. So the idea is to just add edges to C7. Of course, this will guarantee that every vertex has degree at least 2 when we start adding edges. So that's good, but remember we want 3 or 4. So we can't add more than 2 edges to any one vertex. And we need to add at least 1 edge somewhere and at least 2 edges somewhere else. And here we want at least 3 vertices of degree 2. So you know what I'm going to do is I'm just going to earmark these vertices. I'm going to say, hey, these ones are going to be degree 2. I'm not going to touch those, but I'm going to add edges over in the right half of this cycle to guarantee that we, to make sure that we have a vertex of degree 3 and a vertex of degree 4. So, okay, to get that vertex of degree 4, how about I take this one and I add these 2 edges. So let me write down the vertices. Let's see if we're done. 2, 2, 2. Those are those degrees. This one's 4. This one's 2, 3, 3. So let's check to make sure we've satisfied all the conditions. Yep, we have 1 vertex of each of the degrees 2, 3, or 4. We don't have any of any other degree. And we do have at least 3 vertices of degree 2. In fact, we have 4. And so this checks out. That's a construction that works. All right, how about at least 4 vertices of degree 3? I'm going to start again by drawing a 7 cycle. And we want at least 4 vertices of degree 3. So I'm going to take care of those first and then not touch them. So I want 4 vertices of degree 3. How about I do something like, boop, that makes 2 vertices of degree 3 and then another 2 here. So now I have 4 vertices of degree 3. I'm going to not touch those. And I still need a vertex of degree 4. Ooh, so maybe I will have to touch those. because look, I only have 3 vertices, so how can I add edges between those 3 to get a vertex of degree 4? I can't. That's just not going to work. And so how about, notice that if I take an edge here, that'll produce a vertex of degree 3 here, and change this one to a vertex of degree 4. So I haven't altered the number of vertices of degree 3, I still have 4 of them, but now I have that vertex of degree 4, which I needed. And it looks like I'm done, right? Every vertex is degree 2, 3, or 4. There's at least one of each, and I have 4 vertices of degree 3. So that checks out. All right, last one, we want at least 3 vertices of degree 4. I'm going to start with my 7 cycle again. That was a good idea by whoever came up with that, because that'll guarantee every vertex has degree at least 2, which is a nice starting place. At least 3 vertices of degree 4. All right, let's just try and pack some edges in here. I'm going to draw one here to get 2 vertices of degree 3. I'm going to get a vertex of degree 4 there, another degree 3. Here I want another vertex of degree 4. So what do I have so far? I have 4, 4, 3, 3, 2, 2, 2. So I need another of degree 4, and I need a vertex. I already have that vertex of degree 3. So what if I can do what I did back here. I'm going to add an edge from this one to a vertex of degree 3. That'll change that to a vertex of degree 4 and bump this one up to 3. So let's go ahead and add up our degree, or look at our degrees now. So this is 4, 4, 1, 2, 3, 3, 4, 2, 2, 3. So would you look at that? We have 1 vertex of each degree, or at least 1 vertex of each degree. And we have 3 vertices of degree 4. And so that checks out. Pretty cool. All right, this one, we are given the definition of a self-complementary graph. So we know what a complement is. Remember, this is it's the graph that you get when you switch all the adjacent vertices for non-adjacent vertices and all the non-adjacent vertices for adjacent vertices. So anything that's not an edge in the original graph becomes an edge in the complement, and everything that was an edge in the original graph becomes not an edge in the complement. And so with that, let me say something about the relationship between the number of edges in G and G complement. So let's say let M be the size of G, and M, I'm going to call it just M bar, be the size of G complement. Then what do I know about these two things, M and M bar? Well, I know if I take all the edges of G and all the edges of G complement, well, that'll make up, right? That'll be all the edges in G, but then in the complement, those become non-edges, and the edges in G complement are the non-edges in G. And so together, those should give me the size of the complete graph, which is n choose 2. So let's say G order n. So what this is telling me is that M plus M bar must equal n choose 2. The number of edges in the complete graph. And again, so you can see that visually. If you take a graph and its complement and sort of overlay them on top of each other with the same vertex set, you'll get the complete graph. So, okay, so this is telling us some information that'll be useful. For example, if we have a self-complementary graph of order 4, then n choose 2. So, yeah, I should do these solutions in green. I think I started that and forgot. So n choose 2, so 4 choose 2 is 6. And so what this means is that M and M bar have to add together to 6. Now, when I have a self-complementary graph, self-complementary means the graph is isomorphic to its complement. Remember, isomorphisms of graph preserve the number of edges. So what this is telling me is that M equals M bar if a graph is self-complementary. And so that would tell us then, putting these two bits of information together, that whatever self-complementary graph I find, that its size should be n choose 2 divided by 2. So if we have a self-complementary graph of order 4, 4 choose 2 is 6, and so what this is saying, I should have 3 edges. So I can say, we know now that the number of edges in G must be 3, and it's only on 4 vertices, so I'll go ahead and plop 4 vertices down. Now, there's not only just one way to put 3 edges here, right? I could do it in a few different ways. I could put them all off of one vertex. Of course, if I did that, so if I did something like this, then the complement would be a triangle, which is not isomorphic to the blue subgraph there. And so this won't work. So let me try something else. How else can I put 3 edges in here? Well, what if I put them in, what if I make a path? 1, 2, and then how about 3 like that? Then what'll the complement look like? I'll draw it in red. This one would be there, this one would be there, and this one would be there. And so if I sort of unfold that, the complement looks like a path. So the green subgraph looks like a path, and the red subgraph looks like a path. So this is a self-complementary graph. So let me just make that clear. Let G be this graph, P4. Then the complement will also be P4. All right, so how about a self-complementary graph of order 5? Well, let's compute 5 choose 2. So that's 5 times 4 divided by 2. This is 10. And then divide that in half. Half of that will be my size, equals 5. So this is the number of edges in G must be equal to 5. I guess I don't want to necessarily put edges in yet. Let me just draw the 5 vertices. It's 5 vertices of size 5. Now, so once you're at this point, once you have this amount of information, you can just guess and check a lot of different things. What ends up working, and this is actually really special, what I would call a decomposition of K5, is into 2 5 cycles. So here I'm going to let my graph G be a 5 cycle, C5. Then I'm going to draw in blue the complement of this. So that would be an edge, 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 that would be an edge. And notice I didn't touch a vertex more than once there, and that even though it looks, like a star, when I sort of unfurl this and kind of expand it out, that blue subgraph will also be a 5 cycle. I just need to rearrange the vertices, but remember, we know that you can move around vertices and you still end up with an isomorphic graph to the original one. And so both of these graphs are 5 cycles, and so that's self-complementary. So here we'll let G be C5. Oops, not C to the 5th. C5, the 5 cycle. That is a self-complementary graph of order 5. All right, how about a graph of order 7? Well, let's go ahead. So we know that the number of edges in my self-complementary graph must be half of 7 choose 2. What's 7 choose 2? That's 7 times 6 divided by 2, so 7 times 3. So this is 1/2 times 21, which is 10.5. So the number of edges in my graph have to be 10.5. All right, let's start growing. Wait a second. How can I have half of an edge in my graph? I can't. Not really. And so this is what's telling me that this is impossible. So you can't have half an edge. So this is impossible. And that's what I'm looking for there, is to use this theorem. Cool. So in general, you can do this. So if you compute, say, 8 choose 2 or 9 choose 2, you can look at n choose 2. There's only going to be a self-complemented graph of order n so long as n choose 2 is even. And so you can look at that sequence of n choose 2 and see a pattern there of which ones are going to be even. And it follows this pattern of length 4 that keeps repeating itself. And so there is a general theorem here for when a self-complementary graph can exist. I won't go into all of that, but at least we can see that of order 7, no such graph exists. All right, the size of an R-regular graph of order 10 is 30. What is R? So here is another first theorem of graph theory question. If I add up the degrees at the vertices, I should get twice the number of edges. Number of edges is 30. And I know that every vertex has degree R. So that's what R regular means, and I know there's 10 vertices. So these 3 pieces of information will let me get my hands on R. So I know that twice the number of edges is the sum of the degrees of the vertices. I'll just write V and G there and understand that that means all vertices in the graph. And so when I add up the degree, well, every one is degree R, right? So this is the sum over all vertices in the graph, and every degree is R, so that's just R. And so I'm adding up R how many times? Well, the order of the graph, the number of vertices there are. And so this would give me 10R. So I've now summed my vertices, the degrees of my vertices. I get 10R for that, and I know that that has to add up to 60. So I know 60 equals 10R. Divide both sides by 10, I get 6 equals R. And so that's not bad. Yeah, the first theorem of graph theory is definitely your friend. If you're stuck trying to prove something, maybe go back to that, especially if you have information about the degrees of the vertices and you have information about the size. That we'll be able to synthesize some information from that. All right, G regular, G complement is regular. We want to prove that G is regular if and only if G complement is regular. So let me show you something else with a graph and its complement. I'll just pick a graph of order 5. So maybe I have something like this. Maybe that's my graph. And then in blue, I'm going to draw the complement. I just want us to notice something about the degrees of vertices, how these compare to the original graph with the complement. So notice, so the blue edges are the complement, white is the original graph. Notice that every vertex, if I look at the total number of edges, white and blue, so in the graph and the complement, I get 4 everywhere. And that's 1 less than the order of the graph. So why is that? Again, it's because, look, if I look at the white and blue edges here, I have the complete graph on 5 vertices. All of the possible edges are there, and I know in the complete graph, the degree of every vertex is n minus 1, 1 less than the order. And so if I take, let V be in the vertex set of the graph, then let's say G order n, then the degree of V in the graph. So remember, with degree, I can use a little subscript to indicate which graph I'm talking about, if maybe there's a couple graphs going on. The degree in G of my vertex V plus the degree in G complement of my vertex V. Remember, complement and the graph always have the same vertex set. This has to come together to give me the degree in the complete graph of order n of V, which is n minus 1. So I have this relationship. So this gives me a nice tool for this problem. So if my graph is R regular, then the degree of G of V is going to be R for every vertex. And that's going to tell me, I mean, this is constant. This is n minus 1. That n doesn't change from the graph to the complement. We have the same number of vertices. And so we'll be able to calculate the degree in G complement of V. So let's assume G is R regular for some R, and we'll say R is between 0 and n minus 1. It's the maximum possible degree. What that means is that, so for all vertices V in the vertex set of G, degree in G of V is equal to R. Then, well, we have this relationship between the degrees. Degree in G of V plus degree in G complement of V has to add up to give me n minus 1. I know this is R, so degree in the complement of V is n minus 1 minus R. But look, that's true for all vertices. For all vertices, this is true, and so this is true, and so this is true. Hence, G complement is n minus 1 minus R regular. Every vertex has that degree. So that was the forward direction. We assumed that G was R regular. Now, I want you to notice something, that if I take a graph and I look at its complement, and then I take a complement again, so G complement complement, I get back the original graph. So what that means is I can use what I've already proved. So let me do the backwards direction now. So we'll assume G complement is R regular. By what we've already shown, G complement complement is n minus 1 minus R regular. But G complement complement is the original graph, so G is n minus 1 minus R regular. When I was looking at the homework, someone just said it's the same logic both ways, and it absolutely is. And the reason for that is because when you take a complement twice, you get back the original thing. Just like with sets, if I take a complement twice, I get back the original set. It's a very special kind of operation that does that. Okay, I think that's it for 12.1. Let's move on to some stuff from 12.2. I'm going to take a quick pause here. All right, I had a little break. Let's get back to it. So number 2 from section 12.2, we want to show that if G contains a UV path and a VW path, then G contains a UW path. So we're going to use a theorem here that says that if G contains a UW walk, then I can turn that into a UW path. So this is true in general, is that if I have a walk between two vertices, if I have, like, say, an XY walk between two vertices, then a shortest walk is a path. That's essentially how the proof goes, is that a shortest walk is always a path. So if I have a walk, I can produce a path. So what I want to do is take these two paths, the UV path and the VW path, and I want to concatenate them. Right? I go from U to V, and then I go from V to W. The issue here is that, okay, so let's say, let me give myself an example here to illustrate this. Let's call this one U, and this one V, and this one W. So let's say my UV walk goes like this, U to there, or my UV path goes like that. And what if my VW path goes like doot to doot to doot, something like that? And so if I just put these two paths together, I don't necessarily get a path anymore, because those two paths, this one might share a vertex with that one. There's nothing precluding that from happening. It's very possible, and in fact likely, that these two paths share a vertex. And so if I just concatenate these two paths, I won't have a path anymore. I'll have a walk. However, maybe you were looking through the chapter, you found this theorem, hey, a walk, if I take a shortest walk, I get a path. that'll give it to us. So suppose P, and let's just say U, and I'm going to go U1, U2, V is a UV path, and P prime, how about V, V1, V2, up to W is a VW path. We know it might be a walk, so I'm going to call this big W equal U, U1, up to V, V1, V2, up to W, or I should make sure that's a lowercase w, up to W, would be a UW walk. It might be a path, but for sure we can say it's a walk. And we use that theorem that if we have a UW walk, we have a UW path. Hence, there exists a UW path by that theorem. Sorry, I should have had that one. What theorem is this? Theorem 12.26 tells us this. What this is used for, really, is for showing that a disconnected graph is a collection of connected components. So this is how a student proved this one in the homework. Was they said, okay, if there's a UV path and a VW path, that means U and V are in the same connected component, and V and W are in the same connected component, and hence U and W must be in the same connected component, and therefore there's a UW path. So that's I would consider that all right. However, this result that we just proved is kind of used to show that. It shows that this is a transitive property. So two vertices are related if there's a path between them. It shows that that's transitive. It's clearly symmetric, and it's reflexive as well. And so we get a equivalence relation, which splits it into equivalence classes. In this case, the equivalence classes are connected components of the graph. And so that's one way to think about this. All right, let's move on to number 10. Here we're dealing with adjacency matrices. So just to sort of start this one out, I know I did an example in a video before of how to compute an adjacency matrix of a graph. We'll call this one A. So how do I compute an adjacency matrix of a graph? Well, remember I have a row and a column for each vertex. And if two vertices are adjacent, I put a 1 there. And if they're not, I put a 0 there. So I'm just going to set up my matrix like this. Now this is very useful for computing things with graphs, is with an adjacency matrix. There are some better methods, but we won't talk about those in this class. So V1, we assume, no vertex is adjacent to itself because we don't have loops, right? We're dealing with simple graphs here, which are free of loops. So 0 is along the diagonal. V1 and V2 are adjacent, so both these are adjacent. V1 is not adjacent to V3, nor V4, nor V5, so those all get zeros. Let's look at V2. V2 is adjacent to V3, but not 4, not 5. V3 is not adjacent to V1, right? We know that this graph should be symmetric. It is adjacent to V2, and it is adjacent to V4. And then V4 is adjacent to 3 and 5, but not 2 or 1. V5 is adjacent to just V4 and not any of the other ones. So one way you can check yourself to make sure you have the right adjacency matrix is check that it is symmetric. So that is about the diagonal. It is a mirror image of itself. And it is in this case, and so we're set up good. So what this problem is getting at is this theorem that says that if I raise my adjacency matrix to, say, the nth power, that my entries no longer tell me if a vertex is adjacent to another. Instead, they tell me how many walks of length n there are between those two vertices. So, and this one's telling me not to compute a to the fourth. So don't do it by multiplying matrices. We could, and it would tell us number of walks. But instead, we could go the other way. We can count the number of walks, and that'll tell us what a to the fourth is. So we can calculate powers of matrices by counting walks between vertices. So this is I think this is a pretty incredible result, that powers of adjacency matrix tell us number of walks between vertices. It's sort of very surprising. Looking at the proof, I guess it makes a lot of sense, but a priori, it would be difficult to think of this. So those are the results I think are really cool, are the ones that you wouldn't have thought of, but nevertheless are true. Okay, so I'm going to write V1, V2. Let's start computing this. I'm just going to compute part of it, and I guess just kind of let you do the rest. 3, V4, and V5. So sometimes I'll draw my matrix like a little grid, like a little table like this. That's okay. So V1, the V1 cell, that's asking how many walks of length 4 there are between V1 and V1. So how many ways can I do that, get from V1 to V1 back to itself in using 4 edges? And remember, if you use the same edge twice, it's counted twice, and so on. So what are some ways I could do this? Well, I could go to V1, or I could go to V2, then back to V1, and then back to V2, and then back to V1. That's 4 edges, and I returned to V1, and so that's one way. Or I could go to V2, to V3, back to V2, and back to V1. So that tells me are there any other ways to do it? Well, if I go out to V3, or if I go out to V4, there's no way I could get back to V1 in 4 steps. So this is really the only 2 ways of doing it. All right, how about V1 to V2? Is there any way I can do that in 4 steps? So my only option, starting at V1, is to jump to V2. I could go back to V1. That's 1. So let me do this in, how about rainbow pen? So I could go to V2. I have a couple options there. I could then go back to V1 and then back to V2, but I've used 3, and I need to have 4 steps here, and so there's nothing I can do there. So that's not going to work. So let's say I go to V2. What if I go to V3 next? I go to V3. I could go to V4, but then how would I get back to V2? I wouldn't be able to, so I'd have to come back to V2. But then I've taken 3 steps and I'm back at V2. There's no way to get back to V2. So what this is telling me is that there are no ways to get from V1 to V2 with a walk of length 4. And so V1 to V2 is the same as V2 to V1, so I know that this is also 0. Excuse me. Sorry. Right, this should also be symmetric. All right, let's do, I don't know, how about a couple more. So V1 to V3. How can I do that in 4 steps? Well, I could go V1 to V2 to V3. That's 2 steps, and then I could go to V2 to V3. So there's 1. I could go V1 to V2, V2 to V3, V3 to V4, and then back to V3. There's another 1. 1, 2, 3, 4. Any other way I could do it? Well, what if I went V1 to V2, back to V1, and then V2, V3. So there's another 1. And I believe that is all of the ways. So what's nice about this is we can check ourselves by computing a to the fourth. And so I can compute that and make sure that, yeah, that entry should be a 3. And so we can keep going like this, counting number of walks, and we'll get a matrix here that will be a to the fourth. So I'm going to go ahead and end that one. Hopefully you get the idea now, and you can continue to fill in the rest of that. And then you can go ahead and double check yourself by just entering A into maybe an online matrix calculator. You can Google search for one. I use Wolfram Alpha to deal with mine. That's just wolframalpha.com. And you can plug in a matrix and compute powers of it to double check yourself. Okay. Notice if I want closed walks, if I want the number of closed walks between a vertex and itself, I'm looking at the diagonal. I'm looking at the diagonal of this matrix. So that's how I can compute closed walks. All right, let's look at number 14. So this is dealing with isomorphisms and connectedness. So if I have two graphs that are isomorphic, and one of them is connected, does the other one have to be connected? This was actually phrased as a question, but I'm just going to write it here as yes. Yes, if two graphs are isomorphic and one is connected, then the other must be connected. So what this is telling me is that connectedness of a graph it's a structural property of the graph. It's something that's preserved by isomorphisms, and we want to show that. So the key here is that isomorphisms preserve edges. So in proving this, let's write proof here. So we'll assume G and H are isomorphic. Let phi from vertex set of G to vertex set of H be the isomorphism. So remember, this is a bijective function that preserves edges and non-edges. So if I have an edge in G, if I look at the image of those vertices in H, they will be adjacent if they were adjacent in the original one, and non-adjacent if they were non-adjacent in the original one. So it preserves edges and non-edges is what we say there. That's all an isomorphism is. But that's the key, is that it preserves edges, be the isomorphism. So we also want to assume G is connected. So what does connected mean? It means that between any two vertices, there is a path. So let U and V be in the vertex set of the graph. Then since G is connected, there is a UV path. Let's write out that path. So say P equal, so it goes from U to V. So U, I don't know, how about I use U1, U2, up to V is a UV path. So just give yourself an arbitrary path between U and V. And what I want to do is look at the image of this path in H under phi. So then phi of U, phi of U1, phi of U2, and so on. So I look at the image of each one of these vertices up to phi of V is a phi of U. I want to put a dash there instead. Phi of U phi of V path. So that is, if I have a path between two vertices in the graph, then the image of that path will be a path in H. Hence, if there's a vertex, or if there's a path between any two vertices in G, then there's a path between any two vertices in H. It's a UV path. Hence, there is a, let's say, XY path for every two vertices X and Y in the vertex set of H. So that's the key here, is that the isomorphisms preserve edges, and hence they preserve paths. And that's all connectedness means, is that between any two vertices, there's some path. So that will be preserved by isomorphisms. That is, connectedness is preserved by isomorphisms. It's a structural property of graphs. So that's it. I'll consider that one proved. All right, so here's one just thinking about connectedness again. So if I have this graph of order at least 4, and the first part we're going to assume U and V are vertices of G and that they are adjacent. And we also have this, that the degree of U is the same as the degree of V, is n minus 2. And we want to know, is G guaranteed to be connected if we have this? So let's start drawing this out. So I have 2 vertices that are adjacent, and each is degree n minus 2. So here's my 2 vertices in my graph. That means I have n minus 2 other vertices down here. So I'll just draw a big blob to indicate that this is some blob containing a bunch of vertices, and there's n minus 2 of them. So U and V have degree n minus 2, but there's already an edge between them. So U has n minus 1 vertices going down to this blob. Maybe I'll call this blob S, so I have something to refer to. So there's n minus 3 edges from U down to S, and n minus 3 edges down from V to S. So is it necessarily connected? Well, maybe let's look at a specific example. So let's say n is 5. As long as we can find one counterexample, we're good, right? So it's okay to just pick an n and see if that works. U and V, they're connected. They have a degree n minus 2. They have degree 3 here. Here's my n minus 2 other vertices, and each of these has degree 3. So what if the other two edges coming off of U go to those two, and what if the other 2 edges of V go to those 2? Is this graph connected? No, it is an isolated vertex. So the idea here is, in general, we can leave one isolated vertex. I'll sort of separate that from the pack. There's n minus 3 other vertices in here, but since U and V are adjacent, you could just be adjacent to all of those and not this special vertex W. And so W will be isolated in general if I form this construction, but we satisfied all the hypotheses, so this is a counterexample. That's the idea. It does not need to be connected. And we can look at this for a specific example, or in general, this is the construction. We can do that for any order greater than or equal to 4. So what if U and V aren't an edge? So that should tell you something. That, remember, up here it meant U had only n minus 3 other edges down here because U and V were connected. So if U and V are not connected, or not adjacent, rather, sorry, then here's my set S of n minus 2 others. Then since U and V are each degree n minus 2 and they're not adjacent, all of the edges must go down to every vertex in S, and every vertex in S from V. And so then this will clearly be connected. Between any 2 vertices, I can find some path just using U and using V. And clearly there's a UV path because I can jump down there and jump up to V. So that's the idea here is, yes, this will imply it's connected, but no if they are adjacent. All right, moving on. If G is an R-regular bipartite graph, then the 2 partite sets have the same cardinality. So for this one, you might try just drawing some R-regular bipartite graphs and maybe trying for a proof by contradiction, assume they don't have the same cardinality. Just try and make it work, right? So what if my partite sets, I'm going to call them U and W in this problem, standard. So here I have, it's not balanced. They have different cardinalities, 3 and 4. And let's, I don't know, try and make it 2 regular. Is it possible to make this 2 regular? Well, maybe I'll put 2 there. Maybe I'll put 2 there. Well, now those all have 2, so this All right, to make that one 2, it would go there. But then these are sort of stuck now. They would have to go up here, but that would make this not degree 2. So I mean, there's other ways I could have tried that, right? And you might try it a few times and just sort of give up after some point and say, there's no way I can make this thing work. How could I possibly make this work if the two partite sets have different cardinality? So to really get at this, it's sort of a combinatorial argument. I'm going to count the number of edges 2 different ways. So by the first theorem of graph theory, I can add up the degrees of all the vertices. Since it's R regular, that'll tell me something about the size of the graph. And then the other thing with bipartite graphs, I don't have to add up all the degrees of the vertices. I can just pick one partite set and add up the degrees of those vertices, and that'll tell me the number of edges in the graph, because that'll avoid any double counting. So I don't have to have 2 times the edge. This is a special property of bipartite graphs, is that if I want to know the size, I can just add up the degrees in exactly one of the partite sets, and that'll tell me the size. So not twice the size, exactly the size. So let me say proof, and actually let me use green. Proof, let G be in R regular. You might find another way to prove this thing, but this is the way I thought of. R regular bipartite graph, R greater than or equal to 1. And we want to prove that the two partite sets have the same cardinality, so let's give ourselves those partite sets. Say U and W are the partite sets. So my proof strategy here is to add up the number of edges in 2 different ways. So I'll say by first theorem of graph theory, actually before I do that, I want to say, let's say this is order n, G be a graph of order n and U and W. So we know that if we add up the vertices in U and the number of vertices in W together, that should give us n. So that'll be useful. By the first theorem of graph theory, if I add up the degrees of the vertices, and this is over all vertices in the graph, this gives me twice the number of edges. I should say here size m. I should get twice m. Okay, so we know that it's R regular, and so the sum of these degrees would be R times n. So what this tells me then is that R times n equals 2m. N we know is order of U plus order of W, so this is R times U plus R times W, and that's equal to 2m. And then I said there's another way we can find the size of this bipartite graph. How do we find the size of this? Well, we'll just look at one partite set and add up the degrees of those vertices. So we also know, and again, the reason for that is because every edge goes between U and W. There's no edges between 2 vertices of W. And so when I add up all the degrees, I'm not going to double count at all. And every edge goes between U and W, and so I'll hit every edge exactly once when I do that. We also know that the sum of the degrees of the vertices, where V is just in, let's say, W, is the size of the graph. And so we know it's R regular, and so there's W vertices here. So this is R times the cardinality of W is the size. Okay, well, I found the size in 2 different ways. So let me take this and substitute it in up here and see what it tells me. So I have R times U plus R times W equals 2R cardinality of W. So I'm going to subtract R cardinality of W from both sides. I get R cardinality of U equals R cardinality of W. Since R is at least 1, it's not 0, and so I can divide by R. So cardinality of U equals cardinality of W. That's what I wanted to show. The two partite sets, U and W, have the same cardinality. Got it. So that one is admittedly a bit tougher, and you might have come up with another way to do it, and maybe it was even more clever than the way I came up with to do this one. But always remember, you have the first theorem of graph theory in your back pocket, and then there's the special property of bipartite graphs. All right, I think that's, oh, no. No. That's it. That's it for 12.2. Moving on to 12.3, where we'll talk about Eulerian graphs. Going a little slow. All right, so 12.3. Here we're given 5 different graphs, and we're just asked to figure out, is there an Eulerian circuit? Is there an Eulerian trail? Is there neither an Eulerian circuit nor an Eulerian trail? And so I've wrote down the relevant theorem over here, theorem 12.44 from the text. If we have a connected graph with at least one edge, or multigraph with at least one edge, then we know 2 things. We know that G is Eulerian, so that is, it contains an Eulerian circuit, if and only if every vertex of G is even. We also know that the graph will have an Eulerian trail if and only if the graph has exactly 2 odd vertices, so exactly 2 vertices of odd degree. So this is really all we need for this problem. So for an Eulerian circuit, I'm just going to check and see, does every vertex have even degree? That's the same question, really. And then Eulerian trail, are there exactly 2 vertices of odd degree? If not, there's no Eulerian trail. And neither if it satisfies neither of those things. So in G1, notice I have 2 vertices of odd degree. The rest are even. 2, 2, 2, 2, 3, 3. Since there are vertices of odd degree, there is not an Eulerian circuit. However, it has exactly 2 vertices of odd degree, and so this one does have an Eulerian trail. So I would say B, trail. What does that trail look like? Well, we can trace it out real quick. This one's a bit weird, but one thing I can do, that the Eulerian trail has to start at one vertex of odd degree and end at the other vertex of odd degree. So I can go boop, 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 and over and end there. That would be my Eulerian trail. Remember, you're allowed to repeat vertices, but you can't repeat edges, and you have to include every single edge. So check that that blue trail does satisfy that. All right, G2. Well, let's just write down the vertices, the degree of each vertex. So it's 2, 2. Here's a multigraph, right? This is a multigraph because we have 2 parallel edges here. Remember that you count both of those edges for the degree. So this is 4, 2, 2, 4. Here, every vertex has even degree, and so this does have an Eulerian circuit. All right, how about G3? Let's go ahead and look at all the vertices, the degrees of each vertex. Notice down here we have a complete graph on 5 vertices as a subgraph of G3. This part down here. So every vertex here is going to be degree 4, as long as it's not adjacent to anything outside of that. This one's going to change a little bit, but there's 4 to the 4 vertices down there, and then 2 sets of 2. So it looks like this is what, 8, degree 8. This is 2, 2, 2, 2. Every vertex has even degree, and so this does have an Eulerian circuit. G4. Well, look, already we have some vertices of degree 1 and more than 2 of them. So that's an odd degree vertex. There's 4 of them, and so this has neither a trail nor a circuit. Eulerian. G5, we can't actually apply this theorem to G5 because the hypothesis of this theorem is that G is a connected graph or multigraph. Here, G5 is not connected. Remember that a trail and a circuit, any 2 vertices next to each other in the trail or circuit have to be adjacent. And so there's no way to get an Eulerian circuit or an Eulerian trail out of this graph because it's not connected. So this one is neither. right? If you have a disconnected graph, there's no way you're going to be able to find a Hamiltonian cycle, and it won't be Eulerian either, unless I guess the other graph is an isolated vertex. That's a caveat there. All right, let's keep going. So this is asking us to show the complete bipartite graph KST is Eulerian if and only if both S and T are even. So I'd like to use that theorem again. It says a graph is Eulerian, contains an Eulerian circuit, if and only if every vertex has even degree. So complete bipartite graph KST. So that means it's going to look like I'm going to have S vertices up here and T vertices down here. So tell me, and then all the edges possible in between them. That's how you make the complete bipartite graph. And there's no edges between vertices of U or vertices of W. So tell me, what are the degrees of the vertices down here? I'm going to call this U and this W. Then degree of V, let's say for all V in W. Actually, let me change that. Let me call it W. So I just want to notice what the degrees of these vertices are in terms of U, in terms of S and T. So for all, let's say W in big W, what's the degree of the vertex? Well, it's connected to everything up in U, and so it's S. And we can do the same thing for U. For all U in big U, degree of little u is, well, it's the size of W, which is T. So KST Eulerian if and only if. So we need S to be even and T to be even, because every vertex has to be even degree. And so that's it. We use that theorem to say that every vertex has to be even degree, and these are the vertices, that's the degrees of the vertices, so S has to be even and T has to be even. That's it. All right, number 22, we're given, this looks a lot like Bridges of Königsberg problem, but it's slightly different. So this, oh, maybe I should have drawn this. There's a river here. And then there's a river here. So we have these 1, 2, 3, 4, 5, 6 land masses with bridges connecting them. So it's a lot like Bridges of Königsberg. We want to make a graph out of this, or rather a multigraph, and determine, so here it asks us, can we stroll through the city walking over every bridge exactly once? So notice it doesn't say we have to end up back where we started, so we're not looking for an Eulerian circuit. We don't care if this thing's Eulerian. What we're looking for is an Eulerian trail. So for each landmass, I'm actually not going to draw a graph out of this. I'm just going to look at each landmass. How many bridges are there from each landmass? So D, there are 4 bridges. Let me use a different color to avoid confusion. There's 4 bridges from landmass D, 5 from landmass A, 4 from landmass E, 4 from landmass C, 4 from landmass B, and then 3 from landmass F. So we have exactly 2 land masses with an odd number of bridges coming from. So what this tells us is if this were a graph, there would be 2 vertices of odd degree in this graph, or multigraph rather. And therefore we should be able to find an Eulerian trail. Remember, the 2 vertices of odd degree, so landmass A and landmass 5, the trail must go from A to F, or from F to A. So that's giving us a clue as to where to start. And that would be the only way we could take this stroll, is if we started at landmass A or started at landmass F. If we start at landmass C, we wouldn't be able to do it. So if we start at landmass F, let's see if I can draw this Eulerian trail. We can say for sure there is going to be an Eulerian trail, so we could end here, but just for fun, I'd like to draw this Eulerian trail. So I think I'm going to start down here at F, and I'm going to take this bridge, and I'm just going to kind of do a loop around the whole city. So I'm going to go up to D. I'm going to come down to, so we'll just stay in D here. I'm not really taking an edge there, but I'll come down to E now. And then I'm going to go to F again. And I'm going to come out of F and go to C. I'm going to go from C up to E. And really I just got this by kind of doing, process of elimination and just sort of trying some things. Knowing that you have to go from A to F or F to A helps. So once I get to A, I'm going to come down here to C and then come across to B. I've used that edge. So now I've used a bunch of edges, a bunch of bridges, and then I'm going to go up from B to A. And then look, I have these two edges from A to D. So I'm going to go up to D. And I'm going to go down to A. And look, I've crossed every bridge exactly once. So yes, it is possible. And here is such a configuration. It's not the only one. For sure, there's got to be some others. But this one works nonetheless. Notice how all these problems are coming down to that theorem. It's a very powerful theorem. All right, so let's look at 12.4. 12.4 is dealing with Hamiltonian. With this problem, if we have a graph of order n greater than or equal to 3, such that the degree of every vertex is at least n minus 1 over 2, so half of 1 less than the number of edges, which of the following is true? Can we conclude it's Hamiltonian? Can we conclude it's not Hamiltonian? Or is this not enough information for us to be able to tell? Do we have to look at the graph to be able to figure this out? So this is sort of in reference to the theorem that says that if the degree of every vertex is greater than or equal to half of the graph, if you have this degree condition, then G is Hamiltonian. Notice that this is a one-directional implication. It doesn't go the other way. If a graph is Hamiltonian, it doesn't have to satisfy this degree condition. For example, a cycle is Hamiltonian. So remember, here we're looking for just a cycle that goes through every vertex. So clearly a cycle itself will be Hamiltonian. I can visit every vertex exactly once without repeating a vertex. That's what Hamiltonian means, and back where we started. But the degrees of the vertices here are, what, 2, which is not, right? This would be 5 over 2 is 2.5. So this would say if we have a vertex of degree 5 or of order 5, and every vertex has degree at least 3, then it'll be Hamiltonian for sure. But here we can get away with less. And so this, remember, this does not go both ways. It's not true that if a graph is Hamiltonian, it has to satisfy that degree condition. So this one's getting at this. We have almost that degree condition, but not quite. And the idea is, can we conclude anything about this? So it doesn't quite meet the degree condition, so we can't guarantee it's Hamiltonian. But this degree condition, it doesn't go the other way, and so we can't really conclude it's not Hamiltonian either. And so our inclination should be telling us that C, it's impossible to tell. And so to really make this rigid, to really explain why it's impossible to tell, I'll give you 2 examples that both meet this degree condition, where one is Hamiltonian and the other is not Hamiltonian. So thus proving if we have this degree condition, it might be Hamiltonian, it might not be. It's impossible to tell without looking at the graph. So consider this graph G I'm going to come up with. The order is going to be odd. There's something about odd and even order here. We could go further than what I'm going to show you. So I'm going to take one vertex, and then I'm going to have a blob of vertices here and a blob of vertices here. So here's one vertex there. That means there's going to be n minus 1 over 2 vertices here. And I'm actually going to put all the edges. So I'm going to make this guy here a complete graph on that many vertices, k n minus 1 over 2. All these possible edges are here. And same thing over here. This is going to be k n minus 1 over 2. All the possible edges are going to be here, and then I'm going to take this vertex and join it up to every single other vertex. So what we're actually looking at here in terms of operations between graphs is it's k n minus 1 over 2 union k n minus 1 over 2, and then joined with a single vertex, so k1. So I could write this graph, that's the same thing as this. Notice that the degrees of every vertex, so take a vertex down in here, it's adjacent to every other vertex in here, so I'm going to call this v. Degree of v is n minus 1 over 2 minus 1, so that accounts for every other vertex down in this complete graph, but then it's also adjacent to this vertex up here, and so that's plus 1, and so the degree of every vertex in this one is n minus 1 over 2. The same will be true for any vertex here. That'll all have the same, same argument, and then this vertex is adjacent to n minus 1, which is certainly greater than or equal to n minus 1 over 2. So this does meet the degree condition. However, notice that if I delete this vertex, my graph is disconnected. So this is a necessary condition to be Hamiltonian, is it can't contain any cut vertices. I shouldn't, because there's no way for me to make a cycle through all of the vertices without repeating this cut vertex that disconnects the graph. There's just no way I could do it. Right? I'd have to do all of these. I'd have to come over here and then do all these, and then I'd have to come back at some point. So this is impossible. You can't have a cut vertex. This is not Hamiltonian. And yet it does meet this degree condition. So we can say for sure we can't guarantee that G is Hamiltonian. Not true. And then to show you that we can't guarantee it's not Hamiltonian, we'll meet the same degree condition and have it and have it actually be Hamiltonian. So for this, how about I just give you an example? 1, 2, 3, 4, 5, 6, and I'll draw a cycle. So right now every vertex has degree 2. So n here is 6. So n minus 1 over 2 is 2.5. And so if we want to meet this degree condition, every vertex has to be greater than or equal to 3 for all v. So I just want to make sure that degree condition is satisfied. How about here, here, and here? Every vertex has degree 3, so it meets this degree condition, and it is Hamiltonian because it contains a spanning cycle, a cycle that goes through every vertex. And so in both cases, we met the degree condition. One is not Hamiltonian, one is, and so we can't guarantee that it's not Hamiltonian either. And so we have to conclude this is impossible to tell. We'd have to look at the graph. This isn't enough information. That's the deal with that one. All right, are there any others? Yes, one more. So in this problem, we're trying to decide if some of these Cartesian products of graphs are Hamiltonian or not. So this might also help you just compute Cartesian products of graphs because the definition is it's pretty tough to understand. The idea here is, I just have to do it with an example. So I'm going to draw P3 and I'm going to draw P2. Actually, I'm going to draw P3 vertically because it's going to make it look nicer. It doesn't matter how you draw it, of course, but just for illustration purposes. So here's P3, path on 3 vertices. Here's path on 2 vertices. Then the product, so I'm going to actually give names to these, U, V, and W. The product, and let's call this X and Y. So the product of these two graphs has vertex set, the Cartesian product of the two vertex sets of the graphs. So the vertex set of P3 cross P2 will look like, I'll have a vertex called UX. I'll have a vertex called VX. I'll have a vertex called WX. They're ordered pairs. I'll have a vertex called UY, a vertex called VY, and a vertex called WY. And how do I compute the edge set of this? This is the vertex set. How do I compute the edges of this? Well, the definition of the Cartesian product says that two vertices are adjacent in the Cartesian product if they share the same first coordinate and the second coordinate are adjacent in the second graph. So that means since x and y are adjacent in the second graph, these two should be adjacent. Here, these two are both share v, and they're adjacent in the second graph, x and y again. And here again, that would be an edge. And then, do I have any others? Yeah, it also tells me you also draw an edge if the first coordinates are adjacent in the first graph and the second coordinates are the same. So these ones that have x, that end in x, so like this one and this one, u and v are adjacent in the first one, and so these would be adjacent here. Same thing down here. Notice I wouldn't draw an edge from wx to ux because u and w aren't adjacent in the first graph. And then the same thing over on this side. So this is how you can do a Cartesian product of graphs. And this one clearly contains a cycle, right? I can go here. Oh, my drawing pad's messed up. Here, over here, over here, and down here. And so that would be a Hamiltonian cycle in this graph. So this one is yes, this is Hamiltonian. All right, P3 cross P3. I'm going to do the same thing. I'm not going to do it all out like I did before, because hopefully you're starting to see the pattern. So P3 cross P3, I'm going to draw 3 P3s and then connect them according to this P3. So I'm going to go boop, 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 boop. That's P3 cross P3. In general, paths cross paths. Notice how these all look like grids. These are called grid graphs, and they're a nice class of graphs that one can study. So is this one Hamiltonian? Well, let's see. I can go down here, down here, down here, over here. I can go, how can I finish off this one? So this one, I'm getting stuck with the route I'm trying to do because I could come up. I know I have to save this edge for the last one. That's the only other edge that goes to my original vertex. I'd have to save that for the last one, so I could go either up here to this guy and then over, but then I'm kind of stuck, or I could go over and up, but then I'm stuck because then I'd come here and I wouldn't be able to get back to my original vertex. It's looking like at least this attempt is not going to work. So how can I prove this thing is not Hamiltonian? Because now I'm starting to think it's not. It's not Hamiltonian. Well, remember this theorem that says if you can disconnect, if you remove a set of vertices and you're left with more components than what you removed from the graph, than the number of vertices you removed from the graph, then it's not Hamiltonian. Sorry, again, I should have had this theorem ready. This is theorem 12.56. So read through that one. Again, what it says is if the number of components in G minus S, so I remove some set of vertices S, if there's more components in that, then the graph is not Hamiltonian. So I'm using the contrapositive. So actually, I'm really looking at theorem 12.57, the contrapositive of theorem 12.56. If the number of components in G minus S is more than the number of vertices I removed, so the number of vertices in S, then it's not Hamiltonian. So notice if I removed this vertex, this vertex, this vertex, and this vertex, I'll disconnect the graph and it'll be left with a bunch of isolated vertices. 1, 2, 3, 4, 5 isolated vertices. Hence, I removed 4 vertices and ended up with 5 components, and so this one is not Hamiltonian. All right, let's try P3 cross P4. 3, there's 1 P3, 2 P3s, 3 P3s, 4 P3s, and then join them up according to a path. So there's P3 cross P4. And let's see, can I do this one? Can I find a Hamiltonian cycle in this one? Sure, I can. So what if it doesn't matter where we start because it's a cycle. So why don't I start up here, go down here, I'll take all of these edges over here, and then how about I go up to here, and then over 1, down 1, over 1, up 1, and then back to my original vertex. So there's a Hamiltonian cycle. So this is yes. Yes, it is Hamiltonian. P3 cross P5. My conjecture already is that this is going to be not Hamiltonian because both paths are of odd order. I think it's going to have something to do with the order of the paths and more specifically the parity. Here at P3 cross P4, one was even order, and we were able to find a Hamiltonian. Here they were both odd and we weren't. So I'm guessing this one as well is going to be not Hamiltonian. That's sort of in the back of my mind. Maybe I'll be proven wrong. Maybe I'll be able to find a Hamiltonian path here. Maybe not. So let's see. So I could try going around again, and then over, down, up, down. But the parity, see, it's the parity that's going to screw me up if I try and do that. So my inclination is this is non-Hamiltonian, so I'd like to find some vertices that I can remove to split this into a bunch of components. In the last one, I removed those 4 vertices. Let's see if we can do something similar here. So let's just try some things. Let's try removing sets of vertices. So I want to kind of try and follow a pattern like this that I did in the P3 cross P3 case. So how about let's remove this one, this one, this one. Let's remove this one, this one, this one. And how about finally, let's remove this one. So that'll be a total of 1, 2, 3, 4, 5, 6, 7 vertices removed. And when I do that, notice how I've arranged this. Every vertex is then going to be isolated in the resultant graph. How many isolated vertices do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. So here, my cardinality of the set of vertices I removed is 1, 2, 3, 4, 5, 6, 7 is 7. And the number of components in G minus S is, I just counted, 8. And so since there are more components than what we removed, this graph is not Hamiltonian. So in a more advanced graph theory class, I would have you prove that a grid graph is Hamiltonian if and only if one of the paths has even order. That's going to end up being true. And so in general, you'd have to come up with this pattern of which vertices to remove for the odd case, and in general, prove the Hamiltonian case. But in this class, we'll just focus on these 4 examples. As long as we can do it for these 4, I think you're learning it, you're doing pretty good, right? But again, we could generalize past this. Okay. That's it for this video. I know it's really long, so I'm going to timestamp it with all the different problems so that you can locate problems easily and not have to watch the entire thing if you don't want to. All right, that's it for this. See you later.